Hey everyone, and welcome. Today we're going to dive into one of those foundational pieces of the internet that you've absolutely used, but probably never even heard of. It's called the Chord protocol, and it's basically the magic that lets these massive, distributed systems find exactly what they're looking for in a giant sea of data. So, let's pull back the curtain and see how this thing actually works.
So just try to picture this for a second. You've got millions of computers, all connected to each other, and you need to find one specific file. It's kind of like trying to find a single book in a library that's been scattered across millions of separate buildings all over the world, and oh yeah, there's no central card catalog. So how in the world does the system even know where to begin looking? Well, this is the exact problem that Chord was designed to solve.
All right, so here's the game plan for this explainer. First, we're going to look at why finding stuff at scale is so hard in the first place. Then, we'll get into the brilliant idea that solves it, called consistent hashing. After that, we'll see how the Chord protocol puts that theory into practice, how it makes lookups ridiculously fast with something called finger tables, and finally, how the whole system stays up and running even when computers are constantly joining and leaving.
You know, to really appreciate just how clever Chord is, we first have to understand the mountain it was designed to climb. We need to talk about the scalable lookup problem and why the old ways of organizing data just completely fall apart at the scale of the internet.
At its heart, a huge chunk of what the internet does is just finding things. Seriously, think of it like a giant planet-sized address book. Every single time you look up a website, search for a photo in the cloud, or find a friend's profile on a social network, a lookup is happening behind the scenes. It's one of the most fundamental building blocks we have. So if you're a programmer, your first instinct for doing fast lookups might be, hey, why not just use a classic hash table? It's a standard tool for a reason, right? But what happens when your table isn't on one computer, but is spread across thousands of servers that are constantly coming and going?
And here it is. This is the killer problem. With a classic hash table, if you add or remove even one single server, the entire logic for where everything goes can change. You might have to reshuffle and move almost all your data around. I mean, can you imagine telling a company like Netflix they have to move all their movies every single time they add a new server? It's completely unworkable at scale. Okay, so clearly we need a much smarter way to do this, and that brings us to the core concept that makes Chord possible: consistent hashing. It's just a beautifully elegant solution that was designed specifically for this kind of messy, dynamic world.
So what is it, really? Well, imagine a giant clock face. Consistent hashing takes both the things you want to store, your data, and the places you're storing them, your servers, and it gives each one of them a permanent spot on that same clock face. The key is that they all live in the same shared universe, which makes organizing them so much easier.
Now you might be wondering, how does a physical server know where it lives on this abstract clock? Well, it's actually pretty simple. You just take something unique about it, like its IP address. You run it through a hash function, and the number that pops out, that's its one and only position on the circle.
And this brings us to the golden rule of where to put the data. It's kind of like a game of musical chairs. If you have a file that hashes to the 17-minute mark on our clock, you just start at 17 and walk clockwise until you hit the very next server. That server is called the data's successor, and that's where the file lives. This one simple rule is the foundation for literally everything that follows.
Okay, so consistent hashing is the big idea, right? The theory. Chord is the protocol that actually takes that idea and makes it real. Let's see how it takes that circular address space into a living, breathing, distributed system.
The rules are actually really clear and mathematical. Both the servers, or nodes, and the data keys get an identifier of the same length. Let's call it m bits long. A piece of data with a key k is then assigned to its successor. And what's a successor? It's simply the first node you hit whose ID is equal to or greater than k as you travel around that ring.
Okay, let's make this real with the diagram on the screen, because this really makes it click. Look at this simple ring. It's only got 3 nodes, 0, 1, and 3. So if we want to store data with key 1, well, its successor is node 1. Easy. But what about for key 2? We start at position 2, move clockwise, and the first node we hit is node 3. So key 2 gets stored on node 3. Now what about key 6? We start at 6, go all the way around the ring, and the first node we hit is node 0. Simple as that. So how do we find anything? Well, the most basic way is kind of like passing a note down a really, really long line of people. You can ask any node on the ring to find a key for you. That node just passes the request to its next door neighbor, its successor. And that neighbor passes it to its successor, and on and on and on. It'll get there, eventually. But you can already see the problem, right? On a big ring with thousands of nodes, this would take forever.
Yeah, walking from neighbor to neighbor is just way too slow. We need shortcuts. We need a highway system. And this is where Chord gets really clever with an optimization called the finger table. It really is like building an interstate system on top of our local streets. So what is a finger table? It's basically just a small routing table that every single node keeps. But instead of just pointing to its next-door neighbor, its entries are like express lanes. The first entry might be an exit to the next node over, but the next might be a jump a quarter of the way around the ring, and another one might be a rocket launch to the other side of the ring. They point to nodes that are exponentially farther and farther away.
So, with this highway system in place, finding things becomes so much more efficient. When a node gets a request, it just looks at its finger table and finds the absolute farthest node it can jump to that doesn't overshoot the target. So it makes that huge jump. And then, the new node does the exact same thing. Every single hop gets you dramatically closer to where you need to go.
And here's the payoff. The efficiency gain here is just incredible. To find one piece of data in a network of 1 million nodes, you don't have to take 500,000 hops walking from neighbor to neighbor. Instead, it takes something on the order of log n hops. We're talking maybe only 20 hops. It's the difference between walking across the country and just taking a few flights.
And this diagram just illustrates the process perfectly. Let's trace it together. We're sitting at node 1, and we need to find the data for key 26. So, node 1 looks at its finger table and sees it has a finger, a shortcut, pointing all the way to node 18. That's the farthest jump it can make without going past 26. So boom, we jump to node 18. Now node 18 does the same thing. It jumps to node 21. From 21, the next step finds the key's true owner, which is node 28. And that's it. Just 3 hops to cross most of the ring.
All right, so the system is fast. That's great. But any real-world system has to be resilient. Servers crash all the time. New ones get added. So how does Chord handle all this constant change without just completely collapsing?
Well, when a new node wants to join, the process is kind of like starting a new job. First, it finds its assigned desk, its place in the ring. Then it introduces itself to its immediate neighbors, its successor and predecessor. And finally, over the next few moments, it runs a background process to slowly get to know everyone else in the office and build out its own finger table. It's a really graceful, smooth process, not some disruptive overhaul.
And this right here, this connects all the way back to our original problem. Remember how classic hashing made you move almost all the data? Well, with Chord, when a new node joins a system that has n nodes, only a tiny fraction of the data, on the order of 1 over n, needs to be moved. The disruption is absolutely minimal.
And what if a node suddenly just dies? Well, to handle this, each node doesn't just know about its immediate successor, it actually keeps a list of several successors down the line. It's like having backup contacts. It also periodically runs that stabilization function we mentioned, which is constantly checking on its neighbors, updating its pointers if someone's disappeared, and essentially the ring just automatically heals itself. You know, Chord was a landmark paper. It really was. Its ideas about consistent hashing and decentralized lookup went on to influence a whole generation of systems, from the old peer-to-peer file-sharing networks to the modern cloud databases we use today. And it leaves us with this really fascinating question. As we move towards even more decentralized technologies, what core principles from Chord will stick around? And what brand new ideas will come along to build the next generation of the internet?